the University of Arizona BIO5 Institute, we bring together hundreds of multifaceted experts that include world-class bioscientists, engineers, physicians, and computational researchers. This team science approach is designed to ignite creative solutions to the many complex biological challenges facing our families and communities, and has resulted in disease prevention strategies, promising new therapies, innovative diagnostics and devices, and improved food sustainability.
Hello, everybody, and welcome to another episode of Science Talks, a conversation hosted by the University of Arizona's BIO5 Institute. My name is Lisa Romero, and today I'm joined by one of my favorite people who also happens to be my former boss and mentor. He hired me here at the University of Arizona, Dr. Fernando Martinez. He is a University of Arizona Regents Professor, the director of the Asthma and Airway Disease Research Center, and the former director of BIO5. Dr. Martinez is a world-renowned expert and one of the most highly regarded physician researchers in the field of childhood asthma. His groundbreaking research has had an impact on the field in numerous ways, most notably on the concept of the early origins of asthma and COPD. His work now serves as a basis for the design of new prevention and treatment strategies. Hello, my friends.
Hi there, Lisa. Great to see you.
Thank you so much for joining us today.
Please, my pleasure, my pleasure.
I continue to miss you every day, and I'm thankful we have opportunities like this to connect. You and I have had a lot of years of talking and brainstorming and philosophical musing, so this is kind of an extension of that. So
yes, of course.
Excited to have you here. So when I was looking at this and you know, refreshing your bio and all that, I was thinking, how many years have you been at U of A?
Well, I arrived as a postdoc in 1984, so you make your calculation. It's going to be 37
a few years.
37 years. Then I was here for a year as a postdoc, and I left, but I missed too much what the opportunities and the work that I was able to do in that very brief year I spent between 84 and 85. So I returned in 87, and I have been here since then.
That's amazing. I think that's one of the things I loved in talking to you the most is like your historical perspective and just the different things you've been through in your time here. And it makes things very interesting at a university and very valuable. So I want to take like a dive back further into that, because I know a little bit about the origins of your story and why you decided to go into the fields you went into, and sort of how that started very early on in your life. But if you wouldn't mind, you know, talking a little bit about what originally got you interested in studying asthma and specifically childhood asthma and
Sure.
How that related to your life.
Sure. I've told this story several times, but I always love to tell it again because it really marked my life. I mean, I was probably 4 or 5 years of age. I don't remember exactly how old I was when I was awakened in the middle of the night by my dad shouting, breathe in, breathe in. And it was my mother, my late mother, who was having then a very severe asthma attack. And I remember I was in my room, so I opened the door of my room, and I saw that the door of my father's and mother's room was ajar, so I could just see what was going on. I could see my mother struggling mightily to breathe. We had one of those old nebulizers, little bulb, you know, that you used to, hand nebulizer, as it's called, with a little hand pump. And there was my father pumping so that she could breathe, and she tried to breathe and had very great difficulty breathing. And I do remember then that I really promised myself that if I could, I one day would find a cure for asthma. And just these things that little kids tell themselves. And it was ingrained in me for all my life. And fortunately, I have been able to work in the field. I haven't been able to cure asthma yet, but at least I have tried to find new ways in which to prevent it and treat it, which is the final objective of all the work that I do. By the way, my mother survived that attack and lived until she was 84 years of age, but she had asthma all her life.
Yeah, it's such a remarkable story for me, just that that fuel that it put in you, that experience, but also that you kept on that path. I think a lot of us have this, it's hard. That's a difficult path you've taken, and you've worked incredibly hard, and your passion has always remained in that area. I've always really respected that, because I think a lot of us don't do that. And I think it goes to, the things that shape us when we're young. And
for me, it was a lifetime decision. And there have been, and we would take the whole half hour to talk about that, but there have been obstacles of galore along the way. But I have kept my decision. That's what I decided then, and also to be a scientist. What do you know about science at 4 or 5 years of age? You know a little bit. My dad was a pediatrician too, so he did a little bit of science, and I could see him, drawing graphs of work that he had done with his colleagues at the hospital, but they were kind of a distant thing. But my decision was that's what I was going to do, and against all obstacles, I finally was able to do it.
So, the diseases that you've gone on to study, these devastating illnesses, affect millions of children and adults across the world. And you've made so many important contributions, I think, to the understanding of this role of the gene environment interaction. When I first started at BIO5 and you were my boss and mentor, I learned the term microbiome. I did not know what that was prior to joining BIO5, and now it's something I think as scientists you talk a lot more about. But can you talk a little bit about how sort of this thinking, this still somewhat novel path of this gene environment interaction really is driving further discovery in the prevention of these illnesses, and how that works with your strategy and dealing with your projects?
Sure. Well, BIO5 is by definition an interdisciplinary enterprise, and there's few other examples that I know of that are clear about the importance of interdisciplinary research than the discovery of the importance of gene-environment interactions in asthma. What happens is that because of the way we're trained, scientists all over the world, we go in our circle, in our silo, and therefore, for many years, still today, scientists that are experts in the environment study asthma from the point of view of the environment. Scientists that are experts in genetics study asthma from the point of view of genetics. And important discoveries and prevention therapies and new understanding of what causes asthma have come from both environmental studies and from genetic studies. But what we started discovering, and we were among the first to discover that, is that the way these two things really work is that they work in conjunction with each other. They don't work separately. There's no separate environmental factor that determines asthma, because there's always a group of people who is spared from the effect of a negative factor, or who is also, unfortunately, not sensitive to a positive factor. So what determines that people who are exposed, not everybody develops the disease? Well, one of the most important things that determines that is the genetics, and vice versa. What makes people who carry a genetic variant that increases the risk of having asthma? What determines that person, that not all those persons develop asthma, although they have the risk factor? Well, it is that risk factor needs environmental factors to also be there in order to be expressed. So what we came up with is the idea that practically all that can be understood about these diseases will be understood if we put it in the framework of genes that increase the risk of developing the disease if you're exposed to a risk factor, and risk factors that enhance the negative effects or positive effects of a genetic variation. These two things needed to be studied together. And all our work for the last probably 20 years, it always includes these two aspects, because we get, for example, exactly the right group of people who are going to benefit most by a preventive strategy, for example. Not everybody is going to gain with a preventive strategy. We know that. It's by definition that way. And if you put in the potential genetic factors that may enhance the preventive effect of a pharmaceutical product or whatever it is the preventive effect is, you're going to target the right population. And therefore, you're going to not give it to everybody, but to those that are going to be more susceptible to that preventive effect. So this way of thinking, which appears so obvious to me at least, was just not there. People thought, well, we're going to do a prevention and we're going to do it to everybody. Or we're going to, still today, we're going to test the medicine and we're going to test it in everybody. Increasingly, we try to think about this as ways in which we put both things together.
Well, I think, you know, again, words that are more commonplace in science and research today, this personalized medicine, precision medicine, and you can, you know, attach that to anything now, precision aging, precision wellness. And you've had sort of that approach without, you know, the tagline throughout your career ingrained in your thinking. And I think that's why for me, it's always been fascinating, because I think you're right. If you really think about it, it is pretty obvious, but most people weren't studying it that way.
That's the extraordinary thing about innovation. Innovation is always strange, and I have to say opposed, because it is not the way people think up to that moment. What are you saying? Bacteria can prevent asthma? You're crazy. You went bananas. Today, if you say what I just said, of course, I mean, you know, a hygiene hypothesis, all that. It's the way innovation works. It's why innovation is so important, because it goes against what has been thought until then. And that is the important part of innovation. I always tell people, if people don't get very surprised by what you're proposing and oppose it, maybe it's not sufficiently innovative. and
I remember hearing that a few times from you.
Initially, it's not successful because there is an established way of thinking, which has been important for many years. I'm not denying that. I'm part of an established way of thinking now that is going to be obsolete or not as accurate maybe 20 years from now, hopefully 30. So I'm completely retired and it has nothing to do with me. Retired and dead, by the way. But the reality is that's the way we advance. We advance with new ideas. I always say innovative ideas are always crazy. The problem is that not all crazy ideas are innovative. They're just crazy. So
oh my God, I miss your saying so much.
and so you have to have a lot of ideas. And if they're crazy, you just go to the next one. I tell the more junior scientists, don't be afraid of something that looks very crazy. Just test it, see, take a look. And if it's not, go to your next idea. That's how all these things come about. The ways in which you open up thinking to completely new ways of thinking. And that's what happened with gene-environment interactions and what happened with the microbiome hypothesis, which we didn't develop originally, but as soon as I heard about it, they said, yeah, Eureka, and we went from there.
I remember being in a presentation you were giving, and I was there as well, and I think it was for a little bit older demographic of people, I think a foundation kind of event years ago, and it was the first time I had seen you in slides actually talk about how the microbiome might be impacting their health and their children's health and grandchildren's health. And I mean, you went into some detail, and people were just like, you know, their mouths dropped. And I remember just thinking, they've never heard anything like this. And I mean, again, I'll explain a little bit about that, and again, how that sort of infused in this thinking as well.
Yeah, sure. What we have discovered, and I'm going to jump here many, many years of work and puzzlement and frustration and so forth. But what we have discovered is that much like you need to be tested to learn how to walk, your immune system also needs to be tested to develop. We don't come at all with a program made that is going to develop our immune system in the way it needs to develop when you are 5, 6, or 7, whatever it is, the age at which the immune system is already fully developed. We come with a very elementary immune system that is based essentially on maternal influences and on, yes, on potentials of the child, him or herself, but that needs to interact with the environment and needs to learn how to distinguish between danger and friend, between foe and friend. And we don't know that from the very beginning. We know it through the influences of our mother, but ourselves, our own immune system needs to be trained, we say today, for that. In the same way you need to be trained to think, to read, to walk, to everything else. And if you don't train it, you don't get it. And the way to train it is to be exposed. When you decrease exposures, you decrease the capacity of the immune system to be trained. And therefore, the immune system is not capable to distinguish friend from foe and starts thinking that friend or not so bad is horrible and starts overreacting against it because it didn't learn along the way. At the time in which you were also helped by your mother's support. So it's almost like the same thing as walking. Your mother gave you the antibodies, which are, let's say that way, kind of the arms that you know, to which you cling to learn how to walk at the beginning. Same thing here. Your mother gave you her antibodies, her immune memory, quote unquote, and therefore protects you. And in the meantime, your system is learning that this is foe, this is bad. I need to develop all the defenses against this. And this is not. Well, we don't learn that if we're not exposed. And what we think today is that in the last maybe, I don't know, 200 years, 100 years, we have changed the way in which we were raised for the previous 100,000 years, which was to basically be exposed to everything. We didn't even know what a bacterium or a virus is. So you were just exposed. And of course, there were a lot of deaths. We paid a big price for being exposed because we were born, as I said before, with a very immature immune system. On the other hand, when we survived, we were prepared for the world and we knew what was foe and we knew what was friend. What's happening now is that we will have to teach our children artificially to learn what is foe and what is friend, because we don't want to go back to expose our children to all the risks of the world out there. Everybody knows this now with the pandemic. So how are we going to do that? That's the quest, at least our group is on now. What do we need to do to simulate what the microbiome, as it's called, in other words, all the microbes that we're exposed in the environment, this zoo that we're surrounded by, how are we going to replace the effect that they have in allowing our immune system to be trained and mature in the right way? That's what we're into now.
Well, it leads me to a question on some of your studies. I know you've had several and are still involved in several long-term studies, started maybe even pre-BIO5 Institute years, and now, as you've gone on to lead the Asthma and Airway Disease Research Center, I'd love to hear a little bit of an update because of the longevity of, and the potential impact because of that longevity of these projects, the Tucson Children's Respiratory Study and your ORBAC study. What's going on? Where are you? I think that kind of led a little bit into what you were just talking about and what your teams are working on.
Yeah, well, we have a very talented and skilled group of scientists that have been working from different point of view. We're a truly transdisciplinary group. We have a basic immunologist, we have epidemiologists, we have clinicians, we have statisticians, we have a molecular biologist that are all working together at the center around these human-based studies to which we apply all this knowledge together. One of those studies is the Tucson Children's Respiratory Studies has been going on now, funded continuously for the last 41 years. And it's a group of newborns that were initially enrolled, not by me, I was not here then. We were enrolled in 1980 to 84, the year I first came here. And by two scientists, Lynn Tausig and Ann Wright. And they basically enrolled 1,200 children who were still following approximately between 700 of them, 700, 800, depending on who we can contact and find, because they're all dispersed all over the country and all over the world. And for them, we have still in the freezers at BIO5 the cord blood that we collected 40 years ago. It's still been frozen for 40 years. And we're thinking of thawing it right now because we have new technologies have developed in which we, with a very small amount of blood, we can get 7,000 proteins, for example, assessed, which is extraordinary. And we will be able to know if proteins that were present at birth determine the risk for respiratory disease, which is what we're interested in, up to the age of 40 years, which is quite extraordinary. What we're on now is that we studied all the period of growth of the lung, of the immune system, and now we're starting the period of decline of the lung and immune system, which starts around the age of 25 and then keeps on going up to death. And it's very fascinating what we're finding. The factors that determine the maturation of the fetus, for example, just to give you one thing that we're in the middle of today, so I have it very fresh. The factors that determine the maturation of the fetus, or lack thereof, are factors that determine the way in which we age. The placenta has to, at a certain point, age, because that's the way it's going to be able to detach from the uterus and be expelled. And it is very well timed. Certain factors that block aging of the placenta start disappearing, and the placenta starts aging. Sometimes it starts aging earlier and the child doesn't grow during the last period of normal children, but they grow less in the last period because it starts aging earlier and therefore is not as functional, the placenta. Well, those same children who had this problem when they were in utero are the ones that age faster later in life. This is just a very recent discovery we have made. And therefore, because we have data, you asked me for updates on this connection for this very long period, because we had data from when they were very young with their birth weight and so forth. We know that they did not grow very much during the last trimester in the uterus, most likely because of the placenta aging early. These same children age early. In other words, what you had when you were in utero has an influence on what is going to happen when you age. It cannot be done if you don't follow people for 40 years, and because then you have enough perspective to know what is going on. And this teaches us new ways to understand processes like aging of the lung in our case, but I'm sure it's maybe applies to anything else, that may be useful in the future for a better aging. And we just got a major grant, BIO5 was involved in that for aging. This could be ideas that in the future could be used in a better aging. So that's what you can get when you're a patient and follow people for 40 years.
Yeah, that's incredible. And you're right. And one of the things I love about you, about, you know, a lot of our BIO5 researchers and researchers across the U of A is this concept of, like, again, you're not just addressing the current problem. You're thinking, and you're not just thinking in your own realm. I mean, you're talking about aging now. You're an asthma researcher, and I mean, again, when I came to BIO5, that was such an extraordinary concept to me. Is that you know, first of all, you know, your brain never stops either, so we were kindred spirits in that. But also, you know, just where the you know, the linear path can take you with stops and starts and challenges and failures and successes, and also with working with people that you know have different contexts, have different experience, but also have similar goals. And it's quite extraordinary.
That's what truly transdisciplinarity means. That to have an open mind, to pursue discoveries and to pursue collaborators for discoveries that you make that may have an influence on health. That's what we're interested in. And that's the great power of these very long studies, that they connect things that otherwise cannot be connected. We are one whole cycle of life. And what happens at the beginning of this cycle influences what happens at the end of the cycle. It's not that what happens in adult life is independent of what happened to you when you were young. We're just the same cycle up to the very end. And that applies to our brain as it applies to our lungs, as it applies to our other bodily functions.
So another thing we you know, could get into another hour on is the just tiny fact that you're also a physician. You are a practicing physician and have done that alongside of this incredible research career that you have built, and all of the things you've talked about today. You know, for those sort of aspiring physician researchers, which is a tough road, as you described. One of them is tough, much less both of them. Can you talk about, you know, some of the ways, you know, the challenges maybe are a little obvious, but more about the opportunity that you've had because you were able to take what you were learning and actually apply it in a controlled setting?
Yeah, I have the greatest possible admiration for basic scientists, PhDs, who are essential for the advancement of science. I am totally and absolutely supportive, and I was when I was director of BIO5, by the way, to people who do completely useless research, and I say that with tongue in cheek. I am totally supportive for people who want to discover things that don't appear to have any relation to anything practical. Because that's the way knowledge advances. We don't know what we're going to find. We are, you know, somebody said it, I don't remember who said it, but we carry a match in the middle of a completely dark night. And we just, with that little match, we see whatever we have in front of us. And there is a universe beyond that we don't understand and that we know nothing about. Therefore, I'm totally respectful to somebody who goes that way or this way, and maybe they're going to find something marvelous that we don't know about and couldn't even imagine. On the other hand, my role, since I'm a physician, is to solve the problems of the patients that I see every day. That's the way I see myself. And that's the big advantage of physician scientists with respect to everybody else. The basic scientists have the advantage that they may discover relativity just because they want to discover relativity. The great advantage of a physician scientist is that they may discover the cause of cancer or certain type of cancer, or they may discover the cause of asthma, or they may discover the new ways to make a better life for the elderly. We have the patients in front of us. We know what their problems are, and we're seeing them. And therefore, we can address those problems right on and try to solve those problems. So once go from the universe that we can see, I go from the patient I have in front of me. And both are perfectly legitimate approaches. I insist both are legitimate and both are necessary. And the problem we're having today is that it is increasingly more difficult for physician scientists to be able to compete and to be able to succeed because they have so many pressures. The healthcare system has become so complicated, Lisa. And so full of paperwork and requirements and courses and training, and that there's little time for anything else if you want to really be a good physician. So you practically need to work two jobs. You want to be a scientist and a physician. On the other hand, there are still crazy people like that, and like me in this case, who want to do that. And if they are there, we should offer them the greatest possible opportunity. And BIO5 is one of those great opportunities. We need to put this into the brains of the kids that come for keys, that there's opportunity everywhere in science and within the BIO5 enterprise. And one of the opportunities is people who think about the patient in the first place. They have the advantage that they can answer questions that those patients are eagerly needing an answer for.
Yeah, absolutely. And as somebody, as you know, that struggles with asthma, his daughter struggles with asthma, I mean, I have the utmost respect for the fact that you've been able to do that because, we're the patients. Your very long journey to keep all those pieces together and help so many of us that struggle with these, debilitating illnesses. And I'm luckier, my daughter's luckier than most people, but yeah, thank you for keeping that match burning in the forest and continuing on your journey. And I could talk to you forever, and maybe we'll have another chance to some other time get into a little bit more detail, but I don't want to take too much more of your time. But thank you for being just an incredible inspiration to me and thousands of others, if not gazillions, I don't know. I mean, after all these years of people you've trained and mentored and served alongside of and inspired, because it's a real gift that you have to do all that, and I'm very appreciative that at least I was one of those 1,000 people that has benefited. So
thank you so much, Lisa, for the opportunity to talk about my career.
Absolutely. Well, thank you again, Dr. Martinez, for joining us today. And thank you to all of our listeners for tuning in to another episode of Science Talks. For more information, please visit our website at bio5.org. And from all of us at the BIO5 Institute, we'll see you again in the next episode.
Thanks to our listeners for tuning in to another episode of Science Talks. Continue the conversation with us next time as we learn more about the amazing science happening at the University of Arizona's BIO5 Institute.